Hi, this is my video number 37. Alright, I'll talk on the divergence theorem or Gauss theorem. Yeah, also known as divergence theorem. So, in applying the divergence theorem, we need a closed surface. Yeah? For example, if you have a surface like that, for example, alright. So if you consider this the front one as M1, down below we have M2. No, I put M2 the other side, M2, and this one M3 the other side, M4, and top one M5, down below M6. So in this case, I use M as a surface, M1 plus M2 plus M3 plus M4 plus M5 plus M6. That's our M. It's must a closed surface. Yeah, so M basically is a closed surface. Okay, so what does this theorem says? It says that the flux of F, the vector field for the closed surface M, which bound the solid D, is defined as integrate over the surface M F dot N dm. This is volume integral over D. The integrand is given the divergence of F dV. Okay, I think you're familiar with this. Yeah, previous case I use surface, I denote as dm. As S, F dot N ds. Yeah, this is the previous case. I denote the surface as S. Now I use M. We can change that to S to make it consistent, no problem. Okay, but in my note I use for this part I use M, so I put M there. So I give you some example. It's not difficult, don't worry. Much easier than the surface integral F dot N. So let's say we have M. Our F is given as 3x 3y plus z, 3y and z. Okay, and M is given as z equal to 4 minus x squared minus y on the first octant. So determine the flux F. Determine the flux of F. Yeah, that's it. This means the flux of F. So first of all, we need to to use the divergence theorem, so we need to determine what is the limit for D. So to make it clear, we better sketch what is the region, what is the region or the volume D. So given our surface is this, okay, given that surface, now if we plot this, what we can see that this is 3 dimension. So we have those. Okay, always begin with this. Consider on x-axis yz is 0, yz is 0, so x is plus minus 2. So minus side we will not consider that one, so just consider the positive part. Okay, for y-axis we got 4, z-axis we got 4, right? And then consider plane. On xy plane, z is 0, so we have y equal to 4 minus x squared. So we have that. Okay. On xz plane, y is 0, so we have z 4 minus x squared. So we have that. And for yz plane, x is 0, so we have a straight line with negative slope and intersect x0 4. So this, just connect these two lines, 2 points with a straight line. So you have those surface. So our surface is this, okay, including the boundary, that y0, that x0, and z0. Okay, so it's important to identify the region on xy plane. So we need this line. So this line is on xy plane, z is 0, so we have this equation is y equal to 4 minus x squared. It's from the given surface, because z we consider 0 on xy plane. You can determine what is this. This is x is 0, so z equal to 4 minus y, and for this y is 0, so we have z equal to 4 minus x squared. Okay, now having identified those regions, so we can use the divergence theorem. Now we want to evaluate the right hand side of that, so we use that df del dot f, yeah, dv z. Now for the region, okay, we have z from 0 to that surface. So that surface, this surface is given as, z equal to 4 minus x squared minus y. This is given that, which is that surface. Okay, so from 0 to that surface, so that's z from 0 to that surface, 4 minus x squared minus y. Okay, then for y, these two, the last two integral here, yeah, this is for r, where the region projected on xy plane. So on xy plane, you can see y, you can take that from 0, that line, x-axis is y is equal to 0, to that curve. So that curve is 0, that curve is given by 4 minus x squared. And then we consider x from 0 to 2. So x from 0 to 2. Then we identify the integrand, which is del dot f. What is del dot f? Del dot f is, what is this? Del p del x plus del p del q del y plus del r del z. If our f is p q r, yeah, our component of f is p q r, so then del dot f, or the divergence of f, is defined as that. Okay, so we just apply that. So we have del f del x is minus 2x, yeah, minus 2x, plus del f del y minus 1, plus del f del z, yeah, our f, you can write this as a function of f, which is x squared plus y squared plus z minus 4 equal to 0. You can write that. Okay, so by doing that, so if del f here, no, I think I made mistake here. Yeah, sorry. So del f, our f is here. Sorry, I put it here. Our f is 3x 3y z. Sorry. So del dot f. So we have so we have 3 del p del x del q del y is 3, del r del z is 1 plus 1. So dv. So your dv is dz dy dx. Okay, so if you do this, I just skip all the detail, so you will get 896/15. Try this, check. You can justify the solution of this by using the surface integral. Yeah, integrate s or m f dot n dm. You can try this as well. Okay, should give the same solution. I have explained to you how to use that formula. Right, so give you another example. Let's say if I have f is given as xy 4yx squared and yz, where our surface is given as a cube with boundary 1, 1, 1. Yeah, boundary 1, 1, 1 means x equal to 1, y equal to 1, z equal to 1. So if you plot those or sketch those a little bit, you got 1 here, 1, 1. So we have that. Okay, so that's our surface. So this is easy. So you can, to evaluate those, f del dot f dv, that give you x from 0 to 1, y from 0 to 1, z from 0 to 1. Del dot f, so del f del x, del p del x, so you got y plus del p del y, you got 4x squared plus del p del z, you got y. This is d z d y dx. So you just proceed that, you got, I have the answer here is 7/3. Okay, it's not that difficult. The important thing is, given the surface M, we need to identify what that surface. We need to identify the limit of the integration. Yeah, to help you, to assist you to identify the limit of integration is by sketch the volume given. Sketch the solid given. So it will help you. So if I give you this as an exercise, let's say we have D is a solid in the first octet, bounded by we have x plus y plus z equal to 5 and 4x plus 4y plus z equal to 12, and f is given as xz, yz and xy. Yeah, find flux of f. So you don't have a problem to evaluate this, and then you can just substitute into the our triple integral. But what about the limit of integration there? That is surface. So let's try to sketch this. Okay, I have you here. Let's try. Okay, for the first plane here, we have x plus y plus z equal to 5. So everything equal to 5, 5, 5, 5. Alright, so we just connect those points. That. And we have another plane here, 4x plus 4y plus z equal to 12. So for z, we got a bit longer, 12. So let's say that 12. For x, we have 3. So somewhere here 3. For y, we also have 3. We have somewhere here 3. So we have those surface. Okay, that plane. And what is this? Yeah. So our surface is this. Okay, we have those plane and cut by that. We have those plane cut by the second plane. So we have the surface that, okay, cut by that. So we have this. So that's our surface. How to find those equation for that? Just solve equation those things. Let's say this equation 1, this is equation number 2. Solve 1 and 2. Solve 1 and 2. You got in terms of xy, those equation f in terms of x and y is actually the equation that you projected on this equation, projected on that equation. Okay, so in this case you need to divide two regions. First region is those, the second region is that part. Yeah, this is the first region, this is the second region. So which means you need to evaluate d1 f dv plus d2 f dv. Yeah, for d1 is that toward the xy plane, for d2 that toward the xy plane. Okay, you can do that one. I have some more example here. Okay, give you one more example. Let's say if you have f is given as x, y, z, and m is a surface of a sphere. With radius A. So this is not difficult. Radius A. So you know sphere is. So we have those. We have those. So this is our sphere. Okay. That's the radius given as A. Now find flux that's come out from the surface with the given f. Okay, so you know that for a sphere, I have given this the spherical coordinate. You can use x equal to a cos theta sin alpha, y sama dengan a sin alpha sin theta sin alpha sin phi, z equal to a cos phi. This, if you want to use, integrate over m f dot n dm. But if we use the Stokes theorem, Gauss theorem or divergence theorem, so we need to evaluate. We just need to evaluate over region D, F, del F dV. So if you do this, you're going to have 3, because that one will give you 3. That's 1 plus 1 plus 1. That gives you 3. We integrate over the sphere with radius r dv. That will give you a volume of a sphere. Okay, that's volume of a sphere. That gives you volume of the sphere is 4 over 3 pi a cube. That gives you 4 pi a cube. Easy. Okay. You can, of course, if you want to identify the surface, all this surface, you can do this thing. X from what, Z from what, Y from what, and X from what. And then after identify that surface, you can use the spherical coordinates. To identify those surface Z, we know that the surface for the sphere given as what? With radius r, with radius a, we have x squared plus y squared plus z squared equal to a squared. Therefore, for the surface of the sphere. Okay, using this, then you can put it there, and then you can use that, or you can just use that directly. Then you can solve the rest of it. Okay. One last example. Okay, one last example, or I leave it to you as an exercise. So let's see. So D is region or solid bounded by cylinder, x squared plus y squared equal to 4 and z equal to 0 and z equal to 3. And your f is given as is x cube, y cube, x cube, y cube and z cube. Okay. The question is use divergence theorem or Gauss theorem to evaluate S or M, F dot and dm. Okay, so we know Gauss divergence theorem. This is given as triple integral over the region or over the solid dot f dv. So by looking at this surface, I think that's not difficult for you to identify the surface. Here we have x squared plus z squared, and we have those z0 and z3. So if you plot those, so we have, this is a circle with radius 2. So we have circle on xy, then cut on z equal to 0 down there, and then z equal to 3. So z equal to 3, let's say that. So we have okay, so that's our surface. So that's the cylinder. Okay, so therefore those integral d dot f dv, that what you can have from there, you have we have a region D. So if you differentiate those, that f, that give you 3x squared, 3z squared, 3y squared, 3z squared. So we can take out 3. What left is x squared plus y squared plus z squared dz dy dx. Okay, on xy plane is just a circle. So on xy plane you can use r equal to cos theta, y equal to r sin theta, dx dy, that give you r dr d theta. Okay, so from there you can have 3. So we integrate over x, we integrate over y. Now we have changed those things. So this is, you can take it as on theta from 0 to 2 pi, because we consider whole circle, r 0 to 2, because this on xy plane the radius is 2, and z from 0 to 3. Yeah, the height of that cylinder is given is 3. Then x squared plus y squared, this is r squared, z squared. So we have dz, and for these two we have dx. These two we have r dr d theta. We have dz. So we have r dz dr d theta. So you can solve that. You can do the rest. This give you 180 pi. Okay. All right. So with this, all right, with that example, I end up my lecture for this semester. So this will be our last online lecture for the vector analysis. Yeah, any weakness, any lack of concern or whatever it is, I'm so sorry. I think I've given the best to you within the limited IT knowledge that I have, and with help of you, then some of you, then alhamdulillah I can go through all this thing. So good luck for your final exam. If you have any question, if you anywhere of my video that you don't really understand, you can let me know. You can WhatsApp me. Then if necessary, I can explain in term of in the form of video or written notes that I can post in the WhatsApp. Okay, so thank you. Bye bye.